Now we're going to talk about standing waves. And the idea of standing waves is if you have two speakers, so here's one speaker and here's the other speaker, and they're both connected to the same sound source. And this speaker sends the sound source this way, and this speaker sends the same sound source the opposite way. Now we know that these sound waves travel through space, but when they meet each other, moving in opposite directions, the effect is a sound wave. There's some addition at some locations and some cancellation at some locations. And what we get is called a standing wave. It loses that property of traveling. So what you get is called a standing wave. And the interesting feature of standing waves is, so let's say that in the space between these two, let me move it so try to make it clear that that's what we're doing here. And let me move this one over a little bit. Okay, so we are looking at the space between these two waves. And if you track the motion of this wave in between, what you're going to have is these two nodes. Well, it's not necessarily two, but I'm just illustrating an example of what can happen. And you'll have a wave that oscillates inside an envelope between the two nodes. You can think of it as it moves sort of like a jump rope up and down. And then at the nodes, it doesn't move at all. So what we're talking about here is, in this case, you can think of like the displacement of air molecules at a single instant. And so at every instant, at these two node positions, there's going to be zero displacement of air. And if you actually put your ear at these points, you wouldn't hear anything. And so that's a property of a standing wave. At the points away from the nodes, you get oscillations. Well, a lot of musical instruments operate on the principle of standing waves, and we're going to talk about standing waves in two different mediums. So we'll discuss standing waves on strings, like a guitar, a harp, or a piano, and on air columns. That would be like a wind instrument or a pipe organ. And we're going to talk about two possibilities with these air columns. We're going to talk about air columns that are closed at one end, opened at the other end. That would be like a pipe organ. And then the other type we'll talk about is open at both ends, and that would be like a piccolo. Okay, well, we're going to start by talking about standing waves on strings. I mentioned that this represents what happens in guitars, pianos, stringed instruments. It also is what happens within the vocal cords to make sound, to vocalize. And in standing waves on a string, there are not two sources, but you get the effect of two sources. And you get that same effect from the waves reflecting at the two ends of the string. at the two ends. Okay, so if this is the length of a string, okay, and you send a pulse down the string, it will travel from the left to the right, and when it gets to the right endpoint, which is fixed, that point can't move, that fixed point is going to flip this pulse upside down and send it back the other way. And if instead of a pulse, what you have is a wave that's going back and forth, a sinusoidal wave, when these two waves meet each other going in opposite directions, you get an addition of the wave height at some points, a subtraction at some points, and you end up with a standing wave. And we can tell a lot about the nature of this standing wave by thinking about the nodes. So, to understand the possible wavelengths, and eventually to get to figuring out the frequencies, first think about the nodes. And remember, those nodes are the places where there's no oscillation of the point up and down. Okay, so we're going to start with the largest wavelength that's possible, and then we're going to consider all the smaller wavelengths that are possible. And so this first one, I'm going to call the first mode of vibration. And this represents what's called the fundamental wavelength and the fundamental wavelength and the fundamental frequency. Okay, so what's the biggest wave that can exist on this string? And this string has a length of L. Well, we know that the points at the left and the right endpoints are fixed. Those have to be nodes. So the biggest wave you can fit in here has an envelope like this. You can think of it as oscillating between like a sine function and a negative sine function. And so if you think of this as a sine function, this is 2 nodes. That's the smallest number of nodes you can have. What is the length of this wave? Well, notice that this wave, this is the entire string, so the wave doesn't really exist past the end. But if you wanted to get a full wavelength, you'd have to extend this wave another full length L. Okay, now you can see that that's a sine wave that goes through its whole pattern, and now it's ready to repeat. Okay, and so what's the wavelength in this first mode? I'm going to call that 1. And the wavelength is twice as long as the length of the string. And so this wavelength is 2 times L. Now let's go to the second mode. So if this is the length L, the second mode is going to have one more node. So this is the length L of the string. But now there's going to be a node right in the middle there. And in order to have no oscillation at any of these 3 points, the longest wave that you can fit in here is one that goes like this. So this is 3 nodes. And you can see here that if you think of this as a sine curve, there's exactly 1 full wave in that length L. And so in this case, that wavelength for the second mode is just equal to L. And I'm going to do one more of these so you can start to see the pattern emerge. And so for the third mode, each time we're going to add one more node. And so now we have a node here and a node here. And the biggest wave you can fit in with nodes at those 4 places is one like this. So this has 4 nodes. And the wavelength here, you can see that we fit 1 wavelength into 2/3 of the length of the string. So the wavelength here is 2L over 3. Okay, and I'm going to give these names based on which mode we're in. This first mode is going to be called the fundamental wavelength with what's called the fundamental frequency. The second mode is what I'm going to call the first harmonic. Some people call the first mode the first harmonic and so on, but I'm going to do it like this. So the second mode is the first harmonic. The third mode is the second harmonic, and so on. And now, based on these wavelengths that we have for these 3, we can start to figure out an overall pattern for the wavelengths of the different harmonics and the different modes. And so the formula overall that represents these different modes is that the wavelength of the nth mode is equal to 2L over n, where n is 1, 2, 3, and keeps going up. Okay. And you can see that this works if you go back to, so the wavelength of the first mode is 2L over 1. The wavelength of the second mode is 2L over 2, which is just L. The wavelength of the third is 2L over 3, so that formula works. Each one of those wavelengths corresponds to a frequency, and to figure out these corresponding frequencies, we're going to use that distance is equal to rate times time equation that, is maybe our most valuable equation for all of this mode and oscillation stuff. So distance is equal to rate times time, and we can write that as wavelength is equal to v over the frequency. Okay, and so now I can rearrange this, and we see that the frequency is equal to the wave speed divided by the wavelength. Okay, so what's the frequency corresponding to each one of these modes? So the formula for the frequency of each mode now We have an expression for the wavelength of each mode. So we have that. Remember that the speed of a wave along a string is the square root of the tension divided by this mu, which is the mass of the string divided by the length. We talked about that a day or two ago. And so the frequency of the nth mode is equal to, here's our frequency for the wavelength. So it's going to be, I have to take the reciprocal of this because I'm dividing by the wavelength. So I have n over 2L times the square root of t over this mass to length ratio. The fundamental frequency is what we call the note. Okay, so if you're tuning a musical instrument or something, the note that you're tuning to is for f equals 1. So the fundamental frequency, f1, is 1 over 2L times the square root of t over mu. And this is the note. What about all those other, all the infinitely many other harmonics? Well, it turns out that those are always present on the string too, in smaller amounts. And the different amplitudes of those different harmonics are what make up the tone quality of the sound you hear. That's why you can tell the difference between a whistle playing a certain note and a piccolo playing a certain note and an electric guitar playing a certain note and a saxophone playing a certain note. They can all play the same note, but they have these harmonics in different ratios, and that's why they sound different, even though the note sounds the same. Now, to make sense out of this, think about let's think about a bass guitar because it has 4 strings instead of 6 on a guitar. I got to draw less then. So let's think these are the 4 strings. Okay, so this string is a very low frequency, then not quite as low, and then you have a little higher. The frequency is getting bigger as you go from the sky to the ground, and then this one is the highest frequency. And so what's changing here is you can see from the diameter of these strings, the mass per length ratio is the biggest for the one with the lowest frequency. And that makes sense with this formula. If you make the denominator inside the square root bigger, then the frequency gets smaller. If you make the mass per length smaller, like in this 4th string, you make the frequency higher. And then what about fretting the notes? You know, they move their fingers around to make the different notes. Well, when you move your finger around on a string, it adjusts how long the speaking length of the string is. And the smaller you make the speaking length, the smaller you make this L, the higher you make the frequency. So when people play really high notes on a guitar by putting their left hand way up high on the neck of the guitar, the effect is to shorten the speaking length of the string, and that raises the frequency of the fundamental. It raises the fundamental frequency. Okay, let's do an example. Let's say that a guitar string has a speaking length, so it doesn't matter how much of the string is coiled around after it is between the 2 ends of the playing part of the string. What matters is just that part that's between the top of the neck and the bottom the nut, it's called, at the bottom. So the guitar has a speaking length of 0.65 meters. And that speaking length has a mass of 0.00165 kilograms. And the fundamental frequency of that string is 250 hertz. Okay, so we want to know first, what's the string tension? Second, what's the wavelength for the harmonic with 3 nodes? And then third, if you now put your finger somewhere on this string to shorten its speaking length, what's the fundamental frequency of a note with a speaking length of 0.45 meters? Okay, so first of all, to find the string tension, we know that the fundamental frequency of this string is 250 hertz. So we're going to say this fundamental frequency of 250, and then we're going to set that equal to the formula for the fundamental frequency. So remember, here is the formula for the frequency of all the modes. The fundamental is with n equal to 1, and so we just have 1 over 2L, and so the formula is 1 over 2 times L. Now at first we're just talking about the string with its speaking length of 0.65 meters. So L is 0.65 meters. And then we're dividing by the square root of T over the mass per length. Well, let me set this aside for a second and calculate the mass per length. So we have the mass of 0.001625 divided by the length of 0.65. And so this is 0.0025 kilograms per meter. Now go back to the formula that I was in the middle of. The mu value is 0.0025. All this is in the square root. So we can multiply 2 times 0.65 to the 250, multiply that to both sides. Then square both sides, solve for t. So let me write out what I'm doing here. We got the 250. We're multiplying it by the 2 times the 0.65. Then we're squaring all that, and that has to be equal to t over 0.0025. Now solve for t, and you get a tension of 264.06 newtons. So that's the tension of the string. now for the second one, we want to go from talking about the frequency to thinking about the wavelength. And we want the wavelength of the mode with 3 nodes. So let's think about the speaking length of the string. I have 2 nodes drawn here. We want a third one also, so the third node is going to be right in the middle. And now to visualize this, I'm going to draw the standing wave. So it looks like this. The amplitude of oscillations is 0 at each of the nodes. And now think about how long a full cycle of this wave is compared to the length of this string. You can see that if you follow the top one, the sine wave, it goes through 1 full cycle exactly over the length of the string. The length of the string is 0.65 meters. And so the wavelength is equal to 0.65 meters. And that wavelength would be different depending on how many nodes you had, which mode you were talking about. Okay, so now let's say that the player puts their finger down so that the speaking length of this string is 0.45. What is the fundamental frequency of that note? Well, the fundamental frequency is equal to 1 over 2 times the speaking length. So this time the speaking length is 0.45. Times the string tension that now we've calculated. So 264.06 newtons divided by the mu value, the mass per length, which is 0.0025. And if you plug all that into your calculator, you get that the fundamental frequency of this note is 361.11 hertz. And you can see that's a higher frequency, a higher pitch than the string when you play it without putting your finger to shorten the speaking length. The other thing we're going to talk about besides strings is standing waves in air columns. And like I said, we're going to do this calculation for 2 different types of columns. We're going to do, first of all, one that has a closed end at one end and an open end at the other. So one end is open to the environment and the other end is closed. So I'm going to start by thinking about one end open, one end closed. And the way we're going to analyze this, it's very similar analysis to a standing wave on a string, except this time, there are a few differences about what happens, how the wave is reflected, things like that. And now this is oscillations of air molecules. And so these are longitudinal waves we're talking about, not transverse waves. So let's think of the closed end over on the right and the open end on the left. Okay. And we're going to think about the air molecules. What kind of motion do they have in this standing wave? Well, it turns out that air molecules will always have nodes at the closed end. and antinodes, which are the maximum displacement at the open end. And so let's think about what this looks like. And remember, these are longitudinal waves. So now I'm not drawing a picture of what you would see if you drew, if you followed like a video of this wave. I'm just representing, I'm going to make it look like a transverse wave, but the height of this wave I'm going to draw is really telling you about horizontal displacement. Remember that a sound wave is really just air molecules vibrating back and forth along the line that the wave travels. Okay, so there's no displacement here, and there's maximum displacement at the open end. And this has a length L. So what's the biggest wave that you could have that could have a node at the closed end, and an antinode at the open end? And the biggest you could get is something like this. Okay. Well, how much of a wave is that? How much of a full cycle of a sine or a cosine wave is that? For these, it's going to be helpful to think of a cosine wave instead of a sine wave. So think of this red curve that starts at the top. How much of a cosine wave have we gone through? In the length L, we've only gone through 1/4 of a cosine wave. And that means that the wavelength is equal to 4 times the length of this column. Make this look a little more like an L. Okay. So this is the first mode. And again, this is the fundamental frequency and the fundamental wavelength. And now we'll go to the second mode. Well, the column or the tube still looks the same. And we still have a node here. We still have an antinode here. But now, so this one had one node. This time we're going to have, in this length L, we're going to have 2 nodes. And so there's going to be a second node here. And this wave is going to look like this. Okay, so we have big horizontal displacements of air at the opening, then no horizontal displacement of air at this node, the closest node to the left side, then biggest displacements of air at this location, and then no displacements of air again at the closed end. And so what's the wavelength? Well, we've almost completed one full wavelength in the length of this pipe. And so if you break this up into kind of half of, think of the distance from one node to the next node as being sort of one thing. We have a half, another half, and another half. So we have 3 halves of the distance from one node to another. But you have to go from a node to the second node in order to complete a full cosine cycle. So notice this is not a full cosine curve. this would have to go a little bit farther. And so what we have here is a wavelength that's a little bigger than the pipe. And so this is 4L over 3. Okay. If we continued at this end until we got a full cycle, we would be at 4/3 the length of the pipe. And now we go to the third mode. So this is our length L. This time we're going to have 3 nodes. So there's a node here, a node here, a node here, and antinodes at the end and in the middle, in between the nodes. So our graph looks like this. This would be the cosine. You can see that's where it repeats. And we can fit a little more in to our length L. So what's the length of the wave here? If I call from a node to an antinode, one sort of unit, we have 1, 2, 3, 4, 5 of those units over the whole length L. And the wave, one complete cycle of the wave only takes 4 of those units. And so our wavelength is 4 times L over 5. And now based on these 3 modes, we can figure out what the formula is that we're going to see repeating over and over again. So the formula for the wavelengths is that the wavelength, our n wavelength, is equal to 4L over n. But now it's not for every n, it's only for the odd n's. So n equals 1, 3, 5, and it keeps going with the odds. We could keep doing this analysis as long as we wanted, but that's the formula. And you can look back and see that it holds for all of these. For the first mode, we had 4L over 1. For the second mode, 4L over 3. For the third, 4L over 5. And now, just like we did with the string, we can use these wavelengths to come up with the fundamental frequencies, to get the frequencies of the different modes, including the fundamental frequency, which is the first mode. For the frequencies, we know that the wavelength is equal to V over the corresponding frequency. And so the frequency is equal to the wave speed over the wavelength. If we're talking about air, then the wave speed is just somewhere right around 343 meters per second. You could calculate that using the formula that we talked about a couple classes ago, if you had any reason to believe that it was different from 343. And what you get is that the nth frequency is equal to, so we have 343 divided by the n wavelength, which is 343n divided by 4L. And this is for n equals 13579. Okay, so let's do an example problem. what are the fundamental frequency and the first two harmonic frequencies of a pipe with one end closed, so think like a pipe organ, and a pipe length of 1 meter. Okay. Well, to get the fundamental frequency, we're just going to use n equals 1 and use this formula. So that's 343 times 1 divided by 4 times a length of 1. The one in the top is because n is equal to 1. The one in the bottom is because L is equal to 1. And we get a fundamental frequency of 85.75 hertz. Now for the first two harmonics, you're just going to use n equals 3 and n equals 5. And so the frequency with n equals 3 is 343 times 3 divided by 4 times 1. And you get 257.25 hertz. And then with n equals 5, you get 343 times 5 divided by 4 times 1. And that is 428.75 hertz. Now we can do the same analysis for a pipe that's open at both ends. So this time our length L is this. And what's required now is that we have maximum displacement at both of the two ends because they're open. So those are going to be antinodes. And so how can you get a sine or a cosine function to have, and again, let's think of a cosine function. It's easier to picture. So let's think of the antinodes here. We have antinodes here. What's the biggest wave that you can fit, biggest cosine wave that you can fit into this? And the answer is it would have to have a node there. Okay, so you can think of this as 2 quarter wavelengths. And so this is mode 1. This is the fundamental. We have one node. And in order to get a full cosine wavelength, this would have to be twice as long. You know, you can imagine it like, it would have to be like that. And so the wavelength here is 2L. What about the second mode? We still have the same pipe with a length L. We still have antinodes at the ends. But now we're going to have 2 nodes in between. And so this is going to go like this, 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 this. A full cosine function fits exactly into this pipe. You can, if you follow the one that starts on top, you can see that's exactly one cosine cycle. And so the wavelength is equal to L. And this was the one with 2 nodes. Oh my goodness. 2 nodes. And we could keep going with this, but I'm just going to give you the formula. So the formula for the wavelength is that the wavelength sub n is equal to 2L over n, where n is equal to 1, 2, 3, and so on. Okay, and now for the frequency, we know that the nth wavelength is equal to v over the nth frequency. Again, we're talking about oscillations in air, a traveling sound wave in air, so v is equal to 343. And so Fn is equal to 343 divided by the nth wavelength. Now substitute in our formula for the nth wavelength, and you get Fn is equal to 343n divided by 2L. And this is for n equals 1, 2, 3. Okay, so for an example, let's think of a pipe. So say that we know we're going to make a wind instrument out of a pipe, a given pipe, with a length L. If we want the highest possible fundamental frequency, should we have both ends open or only one end open? So to figure this out, we're just going to go back to the formulas. So for one end, we had and we're just doing this for the fundamental frequency. That's what the question's asking about. So look back at the formula for one end closed, one end open. And it's 343 times our n is 1 divided by 4L. So 343 over 4L. The one for both ends open has a fundamental frequency of 343 divided by 2L. So if these L's are the same, which one of these has a greater fundamental frequency? The one with both ends open, which you could imagine is the reason that A piccolo is designed with both ends open because they use that for the highest notes in a band. And the way you can get a higher frequency out of the same length is to have both ends open.